First of all, welcome to third Cryptist. It's my first time here, and I want to thank you, the organizing team. And I also need to thank you, I'll say a thank you to Mustafa Aksöz for inviting me here as a speaker just 3 days ago. As always, it's a good way of making some connections. So it's Furkan. I'm working as a researcher at INCO, and this talk will be sort of a crypto vision talk. I will try to combine some cryptography with some futuristic vision. So I usually make talks around fully homomorphic encryption, use cases, some more technical stuff in the past, but today we will see something different we call transciphering. Before starting, I want to ask who heard about FHE before? That's really cool because the number was very low before. Okay, so FHE, or fully homomorphic encryption, is this actually in a fancy way, but in a plain English, it's more of a encrypt, compute, decrypt cycle, and this is what makes FHE special, because in almost all the other cryptographic modes, we encrypt and then we decrypt after a time interval, but we don't put computation layer in between encryption and decryption. And this is what makes FHE possible. What makes FHE special. What FHE makes possible is computing on ciphertexts. Why this is important and why this is beautiful? Because we use encryption, we used to use encryption, also we still are using to secure some data in storage and in transfers, right? We encrypt something, then we store it, or we encrypt something and send to someone else, and we want to make sure it's securely stored or it's securely transferred. But we had no way of computing on encrypted data till 2009. Craig Gentry came up with the idea of bootstrapping to reduce the noise of learning with error ciphertext to keep on computing on it. In the cycle, the encryption and decryption procedures are done on client side, where computation is done on server side or even on blockchains. So client encrypts, server computes, and then client decrypts. So these are some simple use cases. Private analytics and DB queries are obviously really important for daily technology usage. The second one, machine learning inference on encrypted data. I guess this is one of the most crucial use cases of FHE, because even I know that in many hospitals, even doctors use LLMs to diagnose a patient, which is obviously a very dangerous situation, because they simply give their patients most confidential data to OpenAI. And this cannot be, this shouldn't be possible, and this cannot be normalized. The other thing is the keyword or search over ciphertext, which is really useful in many daily use applications. The fourth one, probably the most relevant one for the blockchain audience, the on-chain confidentiality. The previous talk was on encrypted ERC20s, which is also pretty relevant. It wasn't a fully homomorphic scheme; it was a homomorphic scheme with CK, but FHE is also another way of doing on-chain confidentiality. And the final one, which is I'm excited the most, healthcare. Even in DNA storage, or nucleotide sequencing, or cardiovascular disease risk calculations, you can think of any healthcare-related calculation. All of them are being done on plain text, and have been done on plain text, and will be done on plain text if we don't change it. So, okay, all these are great, making everything encrypted, doing all the calculations on ciphertext, but are everything great? Obviously no. The answer is obviously no, because fully homomorphic encryption schemes like the FHE, CKKS, and the others are not super efficient these days. Obviously, hardware and applied cryptographic, improvements are being done every day, but it's not still that feasible to use in daily lives. But we can reduce these problems in some sense. One of the problems is what we call expansion factor. In most of the FHE schemes, the plaintext ciphertext size ratio is like very small, 1/10, 1/100, 1/1000 in some cases, and this causes the upload, very costly and also increase the latency. So how can we solve this problem? So we can leverage symmetric ciphers, because many symmetric ciphers are of nearly 1x size. They are fast, and they are very well studied from the cryptanalytic perspective. So the core idea is encrypting the data by using a symmetric cipher, and then encrypting the symmetric key with FHE, and then sending the symmetric ciphertext and the FHE encrypted symmetric key to the server, and server evaluates the decryption circuit of the symmetric cipher by using the encrypted symmetric key to the symmetric ciphertext, and the output of that evaluation is simply the FHE encryption of the same message. I'm not sure it's super clear for everyone, because I went through it quite fastly, but we will be here for a couple of more minutes. So, for instance, let's take trivium. I mean, obviously, we're not going to go through the trivium algorithm, but this is one of the symmetric ciphers we know. It's a stream cipher. And like in one of the recent works, they tweaked a bit on trivium, and this is trivium, just a bit different. This is a stream cipher. It's not important, the algorithm itself, but like it's simply a symmetric cipher with the plaintext ciphertext ratio is 1. So the expansion factor is 1. And this is the algorithm that I mentioned, but in more details and in a more legit way. So the first step is obviously, outputting the secret key of the symmetric encryption scheme. So what you see as E is the symmetric cipher. The FHE is FHE, as the name suggests. So the first step is having the secret key of the symmetric cipher. The second step is having the relevant keys of FHE, the secret key, and the evaluation key. This is a private setup for FHE, but it's also really easy to make this on the public setup. So when we sample the keys, in the third step, we take some messages on plain text form, and then we encrypt them by using the symmetric cipher on the fourth step. And in the fifth step, before sending all the things we have to the server, we encrypt the secret key of the symmetric encryption scheme by using the FHE secret key, and we send to server all the ciphertext we have. So these CT0s to CTK are symmetric ciphertext, but the CTSKE is an FHE ciphertext. We send them all these ciphertext to server, and server evaluates the circuit that I mentioned to all these ciphertexts and outputs another ciphertext, which is an FHE ciphertext, but encrypting the same message. So let's now see what actually has changed. In a non-transciphering case, client or user encrypts their message or their data, and then send the ciphertext or ciphertexts to server. Server does the computation on top of it and return the output again as a ciphertext. But the difference is, in the regular case, we have to send these SCSI FHE ciphertext to server, which is a uploading cost and latency, and we say high latency stuff. So we want to outsource all these stuff to server. And in the transciphering case, we simply are sending almost the plain text size ciphertext server. And now it's server's job to convert or transcipher these symmetric ciphers into their FHE equivalents. And yeah, tiny uploads, almost plain text size ciphertexts, and offloading compute to server. What I mean by compute is the transciphering here. It works with standard FHE flows. There are some implementations on CKKS, on TFHE, on BGV, and lower client cost latency. So when when it does make sense to use transciphering is when upload is a bottleneck and if the scheme is flexible to use transciphering with. So obviously limits are this brings extra server compute, and the circuit test matters if it's a leveled scheme. So transciphering is quite a new method in FHE space, like compared to other primitives like the main schemes or like implementations or the hardware work. But I guess it's a really good point, like really good improvement for like user-specific applications. If in a use case users are interacting the protocol, every day, frequently, I guess in these cases transciphering makes a lot of sense. Obviously, it doesn't solve every problem of FHE, but it obviously brings a latency and upload cost solution at some point. So in this talk, I wanted to just meet you with transciphering. Obviously, some of you probably were familiar with that, but I do think that when it comes to FHE, people mostly know about what it is, or its implementations, or how slow it is, and they keep talking on Twitter on how FHE is very, very bad encryption scheme. But I wanted to show you we have different solutions to different side of the slowness of FHE. I hope it was instructive. I hope it was fun, and I would love to hear some questions if you have one.
Thank you very much, Furkan. Very interesting. I have a quick question. So,
please.
With transciphering, we can solve some of the issues about using FHE in their desirable use cases, but not all the problems.
Yeah, that's true. That's true. Because the encryption time is still a problem, compute time is still a problem, and the bootstrapping is the most costly operation to reduce the noise. It's still a problem that transciphering is not relevant with. But yeah, this is more relevant to the upload stuff.
But the additional compute cost on the servers isn't that high, right, compared to what was before? If the bootstrapping is the main thing, they just have to do an additional transformation at the beginning.
I mean, even that is the case, I guess it's not a big problem because in most cases, servers have way stronger computers. So if FHE encryption is a big bottleneck, it would be good that server does it instead of user does it, because user's computer will probably be way weaker.
Okay, thank you. This question?
Sure. This. Yeah, you're right. I actually mentioned that.
Could you just repeat the question, please?
Oh, of course. The question is, why circuit that matters when it comes to TFHE? Because TFHE is not a level scheme. But I actually mentioned that this point is relevant for level schemes like BGV. It's not relevant for TFHE. Yeah, it's an extra step. Transciphering is also something you need to do on your computer, and this is an extra cost for server, but not user.
Thank you. Any more questions? Then, if any questions come to you, there's plenty of time. We've got a break now for about an hour, so just let's say one more thank you to Furkan and go and enjoy some food.
Thank you.